Imagine you have a handful of Lego bricks. You could arrange them into a neat rectangle, say, 2 rows of 3. But what if you have 7 bricks? You can't. You can only make a single straight line. That's the essence of a prime number. They are the numbers that can only be divided by themselves in 1. Think of 2, 3, 5, 7, 11, and so on. They are the indivisible atoms of our number system. Every other whole number, from the humble 6, which is 2 times 3, to a gigantic number with millions of digits, can be built by multiplying these prime numbers together. They are the fundamental ingredients of arithmetic, the very source code of mathematics itself. For centuries, this unique property has fascinated us. Prime numbers are simple to define, but they behave in the most maddeningly complex way. There's no simple formula to tell you what the next prime number will be. They seem to pop up almost randomly as you count higher and higher. One moment you'll find 2 primes huddled close together, like 17 and 19. And the next you might travel through a vast desert of hundreds of non-prime numbers before you stumble upon the next one. In 1859, a German mathematician named Bernhard Riemann, a student of the legendary Carl Friedrich Gauss, wrote a short paper. It was only 8 pages long. It was the only paper he ever wrote on the subject of number theory. But in those few pages, he sketched out an idea so profound, so audacious, that it would change the course of mathematics forever. Riemann was a quiet, shy man, but his mind was a whirlwind of revolutionary ideas. He wasn't just trying to find the next prime number, he was trying to understand the entire landscape of primes all at once. He wanted a map of their territory. Riemann's genius was to look at the problem from a completely different angle. Instead of climbing the number line one step at a time, looking for primes, he decided to fly above it. He built a new mathematical tool, a function, that could give him a bird's-eye view of the whole system. This was a radical shift in perspective. Think of it like this. Instead of counting every tree in a forest to understand its size, Riemann created a way to capture the essence of the entire forest. Its density, its clearings, its overall shape, in a single, elegant equation. So what was this incredible tool that Riemann created? It's called the Riemann zeta function. At first glance, it looks like a fairly straightforward, if-infinite sum. Imagine adding up fractions, 1 over 1, plus 1 over 2, plus 1 over 3, and so on. Now imagine raising the bottom part of each fraction to some power, which we can call s. So you have 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, and on forever. This is the zeta function. It's a machine that takes in a number, s, and spits out another number based on this infinite sum. It seems simple enough, but this function holds a universe of complexity within it. The magic happens when you connect this function to the prime numbers. The great mathematician Leonhard Euler had already discovered a stunning link decades earlier. He showed that this infinite sum was also equal to an infinite product involving only the prime numbers. This is incredible. It means the zeta function acts as a bridge between 2 different worlds of numbers. The world of all whole numbers, 1, 2, 3, 4, and so on. And the exclusive mysterious world of the primes, 2, 3, 5, 7, and so on. It tells us that the primes, in their own strange way, encode the information of all other numbers. The zeta function is the key that translates between them. Riemann took Euler's idea and supercharged it. He wasn't just interested in using whole numbers as inputs for s. He dared to ask, what happens if we plug in more exotic numbers, like complex numbers? These are numbers that have 2 parts, a real part and an imaginary part. This might sound abstract, but it's like moving from a one-dimensional number line to a 2-dimensional map. Suddenly, the zeta function wasn't just a line, it was a vast, sprawling landscape with mountains, valleys, and most importantly, specific points where the landscape dropped to sea level. These points are what mathematicians call the zeros of the function. This is where the mystery truly begins. Riemann found that some of these zeros were easy to find. They were all the negative even numbers, -2, -4, -6, and so on. He called them the trivial zeros, not because they were unimportant, but because their location was obvious and followed a simple rule. But there were other zeros, an infinite number of them, hidden in a mysterious region of his mathematical map. These non-trivial zeros were the ones that held the real secret. They were directly, intimately connected to the distribution of the prime numbers. Where these zeros were located held the key to the prime's chaotic pattern. Having discovered this landscape of non-trivial zeros, Riemann noticed something astonishing. He calculated the positions of the first few of these special zeros, and he found that they all seemed to share a remarkable property. Remember that these zeros live on a two-dimensional map made of complex numbers. Each zero has two coordinates, a real part and imaginary part. What Riemann saw was that for every single zero he could find, the real part of its coordinate was always the same, exactly 1/2. They all appeared to be perfectly lined up on a single vertical line on his map. This is the Riemann hypothesis. It is the simple, bold claim that all the interesting, non-trivial zeros of the Riemann zeta function lie on this one specific line, known as the critical line. It's a staggering claim of order in a place that should be filled with complexity. Imagine you are flying over a huge, dark mountain range at night. Below you, there are countless little lights scattered about. The hypothesis is like saying that you believe every single one of those lights, an infinite number of them, will be perfectly aligned along a single straight road that cuts through the entire mountain range. Why does this matter? Because the precise location of these zeros dictates the music of the primes. The height of each zero along the critical line corresponds to a musical note or a frequency in the song of the primes. The hypothesis claims that the prime number distribution is a perfectly harmonious piece of music made up of clean, pure notes. If even a single zero were to stray off that critical line, it would be like hearing a jarring, out-of-tune note in a symphony. It would introduce a fundamental level of noise and randomness into the pattern of primes that is far greater than we currently believe exists. So far, we have checked for trillions upon trillions of these zeros using supercomputers. We have climbed higher and higher up the critical line, and every single zero we have found has been exactly where Riemann predicted it would be. But this is not a proof. It doesn't matter if you check a trillion, a quadrillion, a googolplex of zeros. There are still infinitely many more that we haven't checked. To prove the hypothesis, you need a logical argument that shows it must be true for all of them, forever. And that is the challenge that has stumped mathematicians for over 160 years. The Riemann hypothesis is not just some obscure academic puzzle. Its importance is so immense that it holds a place in a very exclusive club. At the turn of the new millennium, the Clay Mathematics Institute identified 7 of the most important unsolved problems. They called them the Millennium Prize problems. These are the Mount Everests of mathematics. They've resisted proof for decades or centuries, and their solutions would be major scientific breakthroughs. To spur progress, the Institute offered $1 million for each solution. This list spans many fields: computer science, theoretical physics. Among these titans sits the Riemann hypothesis. It's the only one tied directly to number theory. Being on the list cemented its reputation beyond academia. It became the million-dollar question. Only one of the 7 has been solved so far. The Poincaré conjecture. It was proven by Grigori Perelman. He famously turned down the million-dollar prize. He said his work built on many others. His proof shocked the mathematical world and showed these problems can be conquered. That success renewed the hunt for the other 6, especially the Riemann hypothesis. The million is not the real motivator. The real prize is glory. So, what would actually happen if someone proved the Riemann hypothesis tomorrow? The world wouldn't suddenly change overnight. Our computers would still work. Our bank accounts would remain secure. The immediate impact would be felt most strongly within the world of pure mathematics. It would be like a dam breaking. Hundreds, if not thousands, of statements sit in limbo. Mathematical theorems. Mathematical conjectures. Their proofs often start, assuming the Riemann hypothesis is true. A proof would instantly validate that work. It would trigger a massive domino effect. Entire fields of number theory would move from fragile foundations to solid ground. We'd gain a deeper, more precise view of prime distribution. We could predict how many primes appear in an interval. In any given interval, no matter how large, the error term, our uncertainty, would be as small as possible. The chaos of the primes would be tamed, significantly. But what if it's proven false? That would be even more chaotic, and in some ways more exciting. Somewhere in the zeta landscape, a zero may have gone rogue, a zero not on the critical line. Finding it would be monumental. It would reveal a wilder, more unpredictable universe of numbers. One of the most beautiful ways to think about the Riemann hypothesis is through the analogy of music. As we discussed, the location of the zeros of the zeta function can be thought of as the frequencies or notes that make up the sound of the primes. The overall trend of where primes appear is like the main melody, a steadily rising tune discovered over a century ago. But the fine-grained, chaotic part, why a prime appears here and not there, is like the harmony and rhythm that gives the music its texture and complexity. The non-trivial zeros are the notes of this harmony. The Riemann hypothesis states that these harmonic notes are pure and perfectly tuned. It suggests that the song of the primes is governed by a deep and elegant mathematical structure. If the hypothesis is true, it means that the primes are distributed as regularly and as smoothly as it is possible for them to be. The randomness we perceive is not true, deep chaos, but rather the result of an infinite number of these clean, harmonic waves, overlapping and interfering with one another. It's like the sound of a perfectly constructed orchestra, where every instrument is playing its part in perfect harmony. If the hypothesis is false, it means there is at least one zero off the critical line. This would be like a rogue instrument in the orchestra playing a sour, out-of-tune note. This single dissonant frequency would introduce a new level of jaggedness and noise into the music. The distribution of primes would be fundamentally more erratic than we believe. The difference might be subtle, almost imperceptible over small scales, but on the grandest cosmic scale, it would change the character of the music entirely. It would mean the universe of numbers has a wild streak that cannot be tamed by this elegant structure. This musical analogy captures why the problem is so compelling. It transforms a question about abstract numbers into a question about aesthetics. Is the universe of mathematics fundamentally beautiful and orderly, or is it inherently chaotic and surprising? The story of the Riemann hypothesis is not just a story about numbers, it's a profoundly human story. It's a tale of obsession, of genius, and of the collective, multi-generational effort to conquer a single intellectual peak. For over 160 years, this problem has been a siren's call to the world's most brilliant minds. It has become a rite of passage for number theorists to spend part of their career wrestling with it, testing their mettle against its immense difficulty. The list of mathematicians who have tried and failed to prove it reads like a who's who of mathematical history. Think of the British mathematician G.H. Hardy, who, when crossing the North Sea in a storm, sent a postcard to a friend claiming he had proved the Riemann hypothesis. He reasoned that God would not let him die with such an important discovery unshared, thus ensuring his safe passage. The legendary John Nash, whose life was depicted in the film A Beautiful Mind, was consumed by the problem during his periods of mental illness, believing he was receiving messages from space that held the key to its solution. These stories reveal the deep, personal, and sometimes perilous connection mathematicians feel to this problem. The quest has become a relay race across generations. Each mathematician builds upon the work of those who came before, adding a small piece to the puzzle, finding a new path that turns out to be a dead end, or developing a new tool that allows the next generation to see a little bit further. The development of computers was a game changer, allowing us to verify the hypothesis for trillions of zeros, pushing the frontier of our search further and further into the numerical stratosphere. So why do we care? Why does this abstract question about the location of zeros for an esoteric function continue to inspire so much curiosity, hope, wonder? It's because the Riemann hypothesis is more than just a math problem. It represents the ultimate frontier of human knowledge about numbers. It is a question about the fundamental nature of order chaos. Proving it would not just solve a problem, it would affirm our belief that even in the most seemingly random systems, there lies a deep, hidden, and beautiful structure waiting to be discovered. The quest for a proof embodies the very spirit of scientific and mathematical inquiry. It's about staring into the abyss of the unknown and not flinching. It's about the faith that logic, reason, creativity can unravel even the most tangled of knots. The problem has resisted so many brilliant attacks for so long that it has gained an almost mythical status. Solving it would be a testament to the power of human persistence and intellect.